we're looking at the truth table, the first thing we need to remember is this section here is just where we have all of our different possibilities for P and Q. So when we're talking about the true and the false values, what we've done is we've given ourselves every single possible combination of options. Either they could both be true, they could both be false, or 1 and 1. So each of these 4 scenarios lets us look at all the different possibilities. And remember, P can be any statement that we want, and Q can be any statement that we want. So P can be, I will do my homework, and Q can be, I will go to practice. With our compound statements, we're either talking about them both being true, them both being false, or 1 and 1. And then we need to talk about those situations. Remember, when we talk about statements, we've got 2 kinds. We can have an if-then statement, and that's where we have all the conditionals. Or we can have compound statements, and that's where we have our and and our ors. And that's what we're talking here with our disjunctions and our conjunctions. When I have a conjunction, remember this A is like the A in and our conjunction means that they both have to be true in order to be true. So this is true, but all of these are false. Thumbs up if that makes sense to you. Okay. With our disjunction, as long as something is true, then that sentence is going to carry a true state, a truth value of true. So if you say, look, I need you to go to your practice or do your homework, and you've got one of those things done, mom's happy. If mom says to you, I need you to do your homework and go to practice, then she's only happy if you get them both done. So our or is our disjunction and our and is our conjunction. We follow the order of operations. So we need to do P or Q first, and then this sign here does what to it? What does that sign do? It makes it negative. It negates it. So the cool thing about a truth table is I can make a column and say whatever I want. Turns out, check this out, I've already done P or Q. So this negation sign is just asking me, take this column and tell me what the opposite is. So I can do that. Now the negation is interesting because if you look here at our next column, I'm talking about not P or not Q. So what we might want to do is come over to our original P and Q, and let's add another column and call this not P. Let's add another column and call this not Q. Because not true is false, not false is true. And I can do that for each of these by keeping track of and recording my negation. So when I come over here and I'm looking at not P or not Q, it's going to take the truth value because it's an or statement. All I need is at least one of them to be true for that part of the story. Now you can talk about any single scenario coming from this, and you can say, if I'm not going to do my homework or I'm not going to go to practice, you can see when those truth values have their outcomes. Make sense? All right. For number 2, I want you to consider each of the following statements, and I want you to construct your compound statements. So will you turn to your partner, please? And if P is I will bring my lunch, Q's I will sit outside, R I will share my chips, read to each other what E, F, G, and H mean. Go ahead, turn to your partner and read. Go. All right, so I just did a shorthand of what your conversations were. And I liked hearing the different kids say, oh, don't forget about those parentheses, order of operations. That's where you start. So P and Q is I will bring my lunch and I will sit outside. P or R, I will bring my lunch or I will share my chips. When we look at G, we got to start with I will share my chips and sit outside, or I'm going to bring my lunch. Now you're like, that doesn't make sense. Yeah, but we're just worried about what the combinations of statements are, so don't worry about it. Not or, I'm not sharing my chips, and I'm sitting outside, or I'm going to bring my lunch. Everybody okay with that? Okay. So we're going to skip over 3. 3's on the fold, and we're not worried about that because 3 is a repeat. What is going on? 3 is a repeat of what we did before. There we go. On your homework that we did before, so we won't worry about that. But we will go forward and talk about Vernon High School teachers and their floors. A critical conversation I know you are all deeply concerned about. What kind of floors do people have? Do they have wood or do they have carpet? It is. It's a dicey conversation, so hold on. Hey, 75 people have wood, 54 have carpet, but the crazy thing is 26, what? They have both. So with your partner, I'd like you to have a conversation. If everybody has either wood or carpet, how many people were surveyed? Fill the diagram in with the information and then write a statement showing the disjunction. And your mark is set. Turn to your partner, say, let's go. So the interesting part of this conversation is you got to make sure people aren't double counted. As soon as I put 75 in the wood category, I was 26 people over my tally. Because 75 people said they liked wood, but 26 of them were already considered in the carpet category. Do you know what I mean? So I had to subtract 26 from 75, giving me 49. I had to subtract 26 from 54, giving me 28. Now, if I want to know how many people were surveyed, what do I do with these numbers? How do I figure that out? Add them, Serena says. So we're going to go ahead and add our 49 people that are just wood, our 26 people that are carpet and wood, and our 28 people that are just carpet. I think I'm looking at 103. 103 people. That's how many people I asked the question to. Do you understand about the people that are double counted and why I needed to subtract and how those numbers fit in? I know that was tricky when you saw it before. Does it make better sense now? That's called learning. I want a statement showing a disjunction. Show me with your hands. Is it disjunction this one or this one? Yeah. Your disjunction is going to be this one, so your sentence has to have an or in it. So the diagram shows what? Vernon High School teachers that what? Have wood or carpeting in their house. If you added the number in there, that's fine. 103 people have wood or carpeting. All right, coming back to and reviewing our statements. Our implication talks about if P, then Q. Our inverse, not P and not Q. Our converse, if Q, then P. Contrapositive, not Q and not P. And remember, these two are linked in truth value, and these are also linked in truth value. going to be understanding that that implication is going to be true. If my allowance increases, then I can save more money. Absolutely. The question for you and your partner as you complete these is, can you save more money only if your allowance increases? And that's an interesting conversation. So will you and your partner please fill in these boxes with the words and then decide, is it biconditional? Yes or no? Off you go. Marcus, set, go. So I gave a real short version of my writing. If my allowance increases, then I can save more money. That's my if, P, and Q. And I loved watching Juan Martin talk about it with Scott, where he's like, then you switch it. I saw him using his hands like this. He was talking about the converse. So if I can save more money, then that means my allowance went up. My question for you is, can you save money by another tactic? Is there another way you can save money? Serena says yes. What is it? Okay. Maybe go get a job. If you want to save money, your number one thing is to do what? Spend less. Skip those pumpkin spice lattes. Those are expensive. Right? What people I see walking around with their Starbucks cups, those are expensive. Hey, skip the guacamole on your Chipotle. Right? It costs a little extra. Right? Skip that. You want to save more money, spend less money. So I'm not sure my converse and inverse are true. So can it be written as a biconditional? We're going to go ahead and we're going to say no, because there are other ways for you to save money, or than just relying on your allowance. But for sure, if you're not saving more money, then you know for sure there wasn't an increase in your allowance. Okay, rewrite the following biconditional statement as a conditional statement and its converse. Hey, how do I know that this sentence is biconditional? How do I know it's biconditional? It is. It's a definition. I love it. What else do I see that makes it biconditional? Go ahead. Yeah, it says if and only if. So because I see this, if and only if, I know that it's a biconditional sentence. Would you and your partner please tease it out? Show me the two conversations that happen. What two sentences can you pull from it? Turn it up. Go. And would you agree that both of your sentences are true? Would you agree? Okay. So if two angles are supplementary, then their measure is equal to 180. If the measure or two angles add up to 180 degrees, we can call them supplementary. Sound okay? Okay. All right. So next up. I'm so close. All right. So last time when we were together, you got these notes. If you don't have them out, please take them out. Last time we were together, you got these notes. If you don't have them out, please take them out.
I think we all got these. We all got these, but we didn't get to actually start.
Great. So you got the notes. Take them out. My sentence still applies.
It sounds like a sentence in a children's book. It even rhymes.
Are you with me yet?
See? Drops it into the lake and watches it stay. But it sounds like a children's
When you read it like that.
Exactly. That's my point.
So can we get started? Okay, I'm waiting. All right. Still waiting. All right. So deductive reasoning is an argument that's based on facts. And an argument that's based on facts means it starts with a statement that's given to you that's guaranteed to be true. So the question is, how is this different from inductive reasoning? Inductive reasoning is what we've been doing so far. Inductive reasoning is where you spend your time looking at a pattern, and you observe that pattern, and then you make a conjecture. And after you make that conjecture, you gotta wait and see, is there a counterexample that's happening? So inductive reasoning is based upon patterns that need to be proven. And one counterexample takes everything down. One counterexample ruins everything. So with deductive reasoning, we are now having the idea of, instead of we have to prove something is true, we're given a statement that we can trust is true. There are two rules in deductive reasoning. The first rule is called the law of detachment. And the law of detachment says if you're told if P then Q is a true statement and P is true, then you know that Q is true too. If you've given it as true, then you can trust that it's going to be true. So an example is, if a bunny hops in the room, then I will sneeze. So let's say I'm deathly allergic to bunnies. As soon as that bunny hops in the room, I'm guaranteed to sneeze. If P happens, then Q is guaranteed. Now let's say that you're taking your quiz and I'm walking around and you hear me sneeze. What does that mean? It could be a bunny. It could be that I have a cold. It could be that it's dusty. It could be like maybe like pepper or something else that makes you sneeze, right? So what ends up happening is we end up seeing if P then Q is a true statement and P happens, then you know Q is going to happen. If Q happens, then you cannot go ahead and say that P will also as a result. You can't switch it around. And we know that this is questioning the truth value of the converse. Okay. The law of syllogism, say it. Syllogism, it's a silly sounding word. So with the law of syllogism, it says if P then Q and Q then R are true statements, then P then R is a true statement. So we can say if I finish all my homework, then I know where I need help. If I know where I need help, then I will master geometry. So do you see how I've highlighted where the conclusion of the first sentence is the hypothesis of the second? So we can condense that conversation and link those thoughts through that knowing where I need help. If I finish all my homework, then I will master geometry. And the knowing where I need help is that part that links those two ideas, that first hypothesis and that conclusion. That is the law of syllogism, where it links three ideas together, P and Q and R. So for my 7th period friends, we can talk about this one. If P is, I'm in my favorite class, if I'm in my favorite class, then it's the last period of the day. Here we are, 7th period. It's your favorite class, geometry. The contrapositive, if it's not the last period, then I'm not in my favorite class. Is that a true statement for you? Kristen nods her head and says yes. If it's not the last period of the day, it's not your geometry class. That inverse says, if it's not my favorite class, then it's not the last period of the day. Let me ask you, what do you have 8th period? Is that the last period of a day? Is that your favorite geometry class? No. So if it's not your favorite class, then it's not last period. Well, tomorrow you'll have a class that you don't like nearly as much as you like geometry. Yes. So that inverse statement, not guaranteed to be true. The law of syllogism allows us to combine some statements together. And what I want for you and your partner to do is take a look at these statements and find 3 that are true using the law of syllogism. And your mark it's at top. Make it top. All right, so if a cat's the largest of all cats, then it's a tiger. If it lives in the pride, it can weigh 400 pounds. If a cat weighs 650 pounds, then it hunts alone. Using the law of syllogism. All right, so on the back, what I'd like you to do is take a look at this with your partner. And what we want to do is use our statements. If Roger gets a part-time job, then he'll buy a new bicycle. And what we're given with deductive reasoning is the fact that this is a true statement. We get to understand that we're given truth. And here's our if P, and then here's our Q. If Roger gets a part-time job, then he says he's going to go buy a new bicycle. That's a true statement. Hey, here comes Roger riding on his new bike. Does that mean that he got a job? Yeah. If P is true, then we know Q is true. Is this bicycle a part of our P conversation or our Q? It's part of our Q. So we know that Q is true. Does that mean that P is also automatically true? Is there another way Roger could have gotten that bicycle?
Yes.
Yes.
Yeah. Maybe Grandma gave it to him for his birthday. Maybe his neighbor was having a garage sale and it was super cheap. Right? If Roger gets a part-time job, he's going to go buy a bicycle. Look at that. He's got his bicycle. Did he get a job? Maybe. But was there another way he could have gotten that bike? Yes. So what we're going to say is that this argument is not valid, and the reason why it's not valid is because the law of detachment. The law of detachment does not support the fact that that's true. All right? Let's try this one. If 2 angles are vertical angles, then they are congruent. If 2 angles are vertical angles, then they are congruent. So that is given to us as a true sentence. So let's go ahead and draw some vertical angles because we are told that angles 1 and angle 2 are vertical. So here's our P. If they're vertical angles, then they're congruent. Guess what? Angle 1 and 2 are vertical, so that means that P is true. Can I say that they're congruent? I can say that they're congruent. Yes, I can. I can say that they're congruent because P happened. I can say that Q is true too. All right, with your partner, take a look at the value of x is 7 and x is less than 10. Give me if P then Q, give me if Q then P in words, and decide if it's a biconditional statement. And your mark set go. All right, how's our biconditional doing? Are we true? Is our biconditional true? Lots of heads shaking out there. No, it's not true, because this conversation right here is a problem. Because if we're talking about a number line where I have 7 and all my values of x are less than 7, guess what? It could be 6, 5, 4, 3, 2, 1, all the way down to the negatives and all the rational numbers in between. Oh, not 7. This is 10. X is less than 10. It can be all those different numbers. So this is a true statement, but this is not, therefore not biconditional. All right, so this was kind of fun. Let's read our statements. If Maria is drinking juice, then it's breakfast time. If it's lunchtime, Kira is drinking milk and nothing else. If it's mealtime, Curtis is drinking water and nothing else. If it's breakfast time, then Julio is drinking juice and nothing else. Oh, and by the way, here's a fact. Maria is drinking juice. So given that she's drinking and all those other conditions above, figure out whether A through F, each statement must be true, may be true, or is not true. Turn and talk to your partner. Say, let's go. All right, let's talk about it. Ready? If Maria's drinking juice, which we know she is, then we know it's breakfast time. So because we know it's breakfast time, we know that's true. So if it's breakfast time, then we know Julio is drinking juice, and so we're okay with that. Yes? Thumbs up? All right. Now, is breakfast a meal? All right, so then during all of the meals, Curtis drinks water and nothing else. So breakfast, lunch, and dinner, Curtis is doing nothing but drinking what? Not very healthy. Yeah. Well, he's drinking water. It is very healthy. Good for you, Curtis. Drinking water. Yeah, mealtime could be breakfast, lunch, or dinner. So Curtis has always got his water. Now, Kira's drinking milk. She does that at lunch, but nobody ever told us about breakfast, so we have to leave that open for a possibility. You okay with that? Mm-hmm. Curtis is drinking juice. Nuh-uh. We just said at mealtime Curtis drinks water and nothing else, so that's not going to be true. How about Maria drinking water? We know she drinks juice, but nobody ever said whether or not she drinks water. So who knows? Julio drinks juice and nothing else, so he's not going to be drinking any milk. Who wants to argue? Go.
It says Maria is drinking water, but it says that she's drinking juice.
Right. Can she have 2 drinks? Yeah, she likes a little side of water with her juice, maybe. She's a very thirsty human being. What else do you want to fight about? Come on. Come on, come on, come on, come on. Anybody? Okay. All right. Consider the following statements and conclusions. If an animal is a fish, then it has gills. Now, when it says make a Venn diagram showing that, we can have an argument over what is the subset of the other. Are fish the only animals with gills? Yes, I am. It's clicking. Yeah. See the numbers? Thank you. Because it's recording. watch it and see if it comes back. If an animal is a fish, then it has gills. Are there other animals that have gills? Okay. So that means that gills and fish fit into my Venn diagram like that. If the animal's a fish, then it has gills. If it has gills, is it a fish? No. Now let's talk about our turtle. Our turtle is out here. Here's a little turtle. He doesn't even have gills. Is there any way he's a fish? So that is a good reasoning. All right, here's our next one. If you wake up late, you're going to miss the bus. If you miss the bus, you're going to be late for school. So when we talk about if you wake up late, then you are late for school, the law of syllogism helps us because these two statements are linked by the conclusion of the first statement and the hypothesis of the second. So read A, B, and C, and D and tell me which one is my conclusion. Who's got it? Go. B. If you wake up late, then you are late from school. Is that what you said, B? Raya? Yep. Emery says, if you wake up late, then you're late for school. I like it. Sounds good. Notes are okay, right? All right, now we're going to go back to our sentences. And what I'm going to show you, you and your partner have one of these statements. When you see them all next to each other, one side is clearly inductive reasoning and one side is clearly deductive reasoning. You and your partner can find each of your statements somewhere there. Tell me, what do you conclude? What is your conjecture? Which one is which? Which one is which? Let's go ahead and walk our way through them. Nora likes this story. She thinks it's the beginning of a storybook. Cave person, Stony Rock, picks up a rock, drops in the lake, and watches it sink. He picks up a second rock, drops in the lake, it sinks. He does this 5 more times, and each time the rock heads straight to the bottom of the lake. Stony conjectures, oorah, nope, say blue. Anybody have ticket number 1? What did you say? That translates to what? Mason, go. Okay, which translates to, if it's a rock, then it sinks, right? So Mason says, this rock sinks. Would you call that an example of inductive or deductive reasoning?
Inductive.
Inductive is where we find the pattern, make a conjecture. Inductive reasoning, for sure. All right, let's find number 2. Number 2, nope, back here. Number 2, here. Salesperson Henrietta Cluck is selling square egg makers door to door at first. She tells a joke about robot chicken eggs. She gets a laugh, makes a sale. Second house, she talks about creative cooking techniques. No sale. 3rd, 4th, 6th, and 8th houses, robot joke, makes a sale. 5th and 7th houses, creative cooking techniques, no sale. Anybody in group number 2 want to tell me what Henrietta Cluck might say? Go ahead. So she's going to say, if I make a joke, then I'm going to make a sale. Inductive or deductive reasoning? Inductive. Inductive reasoning. All right, let's try to find 3. All turtles have shells. I've captured a turtle. Therefore, the animal I have captured has a shell. If it's a turtle, then it has a shell. I have captured a turtle, so P is true. So what does that mean? Q is going to be true. Inductive or deductive? This is deductive reasoning. It is my law of detachment. Number 4. Juan goes to a restaurant, eats some sushi. 3 hours later, breaks out a terrible rash. 2 days later, he goes out again, sushi rash. A week later, Juan's the smartest knife in the drawer, sharpest knife in the drawer. A week later, let's have sushi one more time. Same rash. What is Juan's conjecture? Who had number 4?
If you eat sushi, then it is a rash.
Okay, so Juan's like, I'm thinking if I go out for sushi, then I'm going to get a rash. Donovan, inductive or deductive reasoning? Inductive reasoning. It's the pattern that he found. All right, let's go try to find 5. If it's raining, the ground is wet. It's raining, therefore, group 5, what would you say?
The ground is wet.
The ground is wet. Here's my P. Here's my Q. I just found out my P was true. So guess what? My Q is going to be true. Deductive reasoning, law of detachment. Number 6. All creatures need water to live. I'm a creature, therefore I need water to live. What conjecture might you make about the difference between inductive and deductive? Look at all the words. Mathematician lands at the airport of the Kingdom of Moravia. Sound like a story? Hey, let me tell you what happens. He desperately needs to use the bathroom. He's shy, not sure the social customs in which door to go in. He locates the doors to what appears to be bathrooms. He watches men go into one, women go into another. He's got to figure out which one to go in. Inductive or deductive reasoning? Inductive reasoning, he's got to make a conjecture. Could he be wrong? Absolutely, right? Your conjecture is always up for argument, not always true. Hey, I want to talk to you about this last one. We had 3 examples of law of syllogism. No, law of detachment. This is a law of syllogism. Are you ready? If it's a cat, then it's a mammal. And by the way, no mammals are insects. So I can say no cats are. And this is going to be deductive reasoning by my law of syllogism. Okay? Sound okay? All right. All right, so today's notes are where we're going to really dive deeper into deductive reasoning. And we're going to use the deductive reasoning to prove what you already know. Algebra. Right? Because you all know algebra, right? Say yes. Yes, you all know algebra. Okay. When you were in algebra, you learned how to solve equations by using your properties of equalities. You were able to add the same thing to both sides of an equation, subtract the same things from both sides of an equation, multiply and divide the same things from each sides of the equation. In geometry, we are okay with you abbreviating the addition property of equality, your subtraction property of equality, your multiplication property of equality, and your division property of equality. So in your justifications for your algebraic solving steps, you are allowed to use those abbreviations. When we start talking about some of the other properties that you learned in algebra, some of the properties were actually not of equality, but properties of real numbers. And these properties of real numbers were the rules that let you manipulate and finagle things on just one side of the equal sign. If you wanted to add or multiply in a different order, the community property let you do that. If you wanted to change the grouping of addition or multiplication, the associative property let you do that. Your inverse always gave you your identity. The distributive property and combining like terms were ways that you could simplify once you follow the order of operations. So as a little side note about the distributive property, a story I like to share is of a 6th grade Tracy who was in her math class feeling like she knew more than the teacher. So the teacher started off with this lesson one day saying, students, when we follow the order of operations, you do what's inside the parentheses first. Tracy, can you solve this for me? And I said, well, 5 plus 3 is 8, 2 times 8 is 16. Very good, nice job. I'm feeling like I'm on top of the right because I answered the math question. That's perfect. The next lesson, Tracy wasn't listening. It happens. And the teacher says, Tracy, can you solve this? And I'm like, boy, is she off her rocker. We just did this yesterday. So I said, well, 5 plus 3 is 8. 8 times 2 is 16. And she said, no. I'm like, what? And she says, 2 times 5 is 10. 2 times 3 is 6. The sum of which is 16. And I proceeded to say, that's the dumbest thing I've ever heard. Just yesterday you told us something completely different. How was I to know that's why would anybody spend more time doing all those calculations? You're too stupid to have this job. So when my mother picked me up from the principal's office and asked me what happened, I was very indignant that teacher had no idea what they were doing, because why would I spend my time doing this math when this was possible? Do you see my point? So when we try to teach the distributive property of multiplication over addition and subtraction in the elementary schools, the kids get very confused by it. Fast forward to when I'm sitting in algebra and the teacher shows me this and says, Tracy, can you simplify that? And I say no. Because I can't add x and 3 because I don't know what x is equal to. And the teacher says, have you not heard of the distributive property? And I'm like, oh. Now I know why we need the distributive property, because I can keep going here when I could not here. I do feel badly like I owe that teacher an apology for my mouthing. Our distributive property of multiplication over addition and subtraction is a hugely important tool in how we go ahead and we simplify. And I am fine with you calling the distributive property DP Don't get that mixed up with division property of equality. It's not a property of equality. It just allows us to take this coefficient and distribute it to each of our terms that we're adding so that we can keep going. Now, in my years of teaching algebra, we definitely talked about the substitution property of equality, and we even gave it its own abbreviation, subco. Make sure you don't get that mixed up with SCO for subtraction. The substitution property of equality says if A and B have the same value, you can substitute one in for the other. Just like when I'm not here, a substitute comes in and does my job. I'm not sure that you ever learned reflexive, symmetric, or transitive. Anybody want to tell me yes you did, or do you agree with me? Did you ever? So this reflexive, symmetric, and transitive properties, they're kind of basic. For any real number, it equals itself. For any, if A is equal to B, then B is equal to A. And if A is equal to B, B is equal to C, then A and C are equal to each other. And this might remind you of what we just talked about. And it might remind you of the thinking involved in the law of syllogism. We're not going to spend too much time on them in terms of algebra, but we will translate down here and talk about them in terms of geometry. Because these are where the properties really come into play with geometry. And I want to make sure that you understand anytime I'm talking about a numerical value, I'm talking about equality. Every time that I'm talking about an actual physical thing, the angle or a segment, I'm talking about congruence. Things are congruent, values are equal. And what you'll notice is the reflexive, symmetric, and transitive properties, along with algebra, come down to both of these geometry ideas. So we're good. Here it goes. Hey, for any segment, AB, the distance from A to B is the same as the distance from B to A. That's my reflexive property. If I want to talk about it in terms of angles, for any angle A, the measure of angle A is going to be equal to the measure of angle A. Reflexive property. Think about a mirror looking at the reflection. Everything is equal to itself. For my symmetric property, if the distance from A to B is equal to the distance from C to D, then that means that the distance from C to D is equal to the distance from A to B. I took that equation and I spun it around. If you were one of my friends who every time you solve for X, if you ended up with X on the right-hand side of the equation and you wanted to flip it around, the symmetric property is for you. If the measure of angle A is equal to the measure of angle B, well then the measure of angle B is going to be equal to the measure of angle A. My transitive property sees the distance from C to D is the common link here. So if the distance from A to B is the same as C to D, and the distance from C to D is the same to E and F, then the distance from A to B is the same as the distance from E to F. That transitive property can also help me link my measures of angle A and angle C because they were both equal to B. Those same conversations can be translated into talking about segments. If I have segment AB, that's going to be congruent to segment BA. Whether I take a look at that piece from left to right or right to left, that segment, that physical thing is the same. And angle A is going to be congruent to itself. Notice the difference between when I'm not talking about its numerical measure. I include the segment above my segments, and I don't talk about the measure for my angles. So these ones are written for you. My symmetric property flips it around, and my transitive property goes ahead and recognizes if there's a common link in the hypothesis and the conclusion, then I can go ahead and link those other two together. These are all properties that we're going to be using in our proofs. For all the people that are like, oh, geometry is terrible because of all the proofs, you'd be like, wrong, you just didn't know how to do them. Because the proofs are all about winning an argument, and everyone I know wants to win an argument. We're going to use deductive reasoning, and we're going to logically show why each conjecture is true. We're going to use definitions, postulates, and laws of logic. We're going to learn it in two different formats, 2-column and paragraph. Turn over to the other side of the paper. We're going to start doing this with something you already know how to do. Solve an equation. Your statement is always going to be first, and your statement is what are you doing? Your justification is going to come second, and your justification is like, who says you can do that? Why are you doing that? The very first justification that we always have is given. So it's like, hey, I'm doing this problem. Why are you doing it? She gave it to me. That's a given. Each step that you do in solving gets a justification. So for my first step, 6 times x plus 12 is equal to negative 3x plus 30. Who says I'm allowed to do that? And what did I do? I distributed that coefficient 6 across to each of my terms that's being added. Now this one's kind of nice because it tells us what to do next. I need to solve this, and I'm going to be doing it by adding the same thing to each side. What would you like to add in order for me to solve this next? What should I add? Go ahead, Cole. Yeah. Let's go ahead and combine our x's and call this 9x plus 12 is equal to 30. How come I can do that? My addition property of equality says so. Next, it tells me I'm going to be subtracting. Subtract 12 right here. Next, it says I'm going to be dividing. What am I going to be dividing? So use the properties to justify each step. So from the front of the page, I looked at each of those properties, and I can say which one's going to help me solve it. All right. This next one says, use the information to find the measure of angle 1. So keeping with the same, our first justification is always going to be our given, and we can fill in what we know. The sum of all of these angles is 360. There it says it. 2 plus 3 is equal to the measure of angle 4. Measure of angle 1 is equal to the measure of angle 4. So that's what we're given. That's that information that somebody said, hey, I've got a bunch of stuff to tell you. Here it goes. Ready? They're like, okay. Go ahead.
How do you know that 2 and 3 equal 4? Oh, okay.
2 and 3 equal 4, and 1 equals 4. That's all the stuff that was given to me. So here's something pretty cool that I can do. Instead of writing the measure of angle 1, I'm going to write the measure of angle 4. Instead of writing the measure of angle 2 and 3, I'm going to write the measure of angle 4. So I was able to use the substitution property of equality to write each of those things in instead of what was originally there. When I go to simplify, we can also sometimes call this combining like terms. Because measure of angle 4 plus measure of angle 4 plus measure of angle 4 is going to be 3 times the measure of angle 4. That means that my measure of angle 4 is going to be 120 degrees, says my division property of equality. Why are you allowed to do that? I divided each side. Okay. Now here's the interesting thing that I want you to see. Up here, I said that the measure of angle 1 is equal to the measure of angle 4, and I just found out the measure of angle 4 is equal to 120 degrees. My question for you is, do you see your common length? So what is the measure of angle 1 equal to? It's going to be equal to 120 degrees, and that transitive property of equality, and we can go ahead and call that the transitive property of equality, told me so. So when you're doing a proof, what you're doing is you're just proving to everybody, this is what I know, and this is how I know it, so nobody can argue with you. Your algebraic properties can be also used with segment properties. Will you please check your worksheet and make sure that you change it to BC equals 22. Yours says BD equals 44. We're changing that.
What do we write?
BC is equal to 22. All right, given the diagram, C is the midpoint of BD, BC is 3x minus 8, CD is x plus 12. This is what we need to prove. So our first step is always to write what we know is true. The first thing that I know is true is C is a midpoint of segment BD. I know the distance from B to C is 3x minus 8. And I know that the distance from C to D is equal to x plus 12. Let's talk about what this means. If C is the midpoint of BD, are you okay with this being equal to that? Yes? So if BC is 3x minus 8 and CD is x plus 12, think for a minute about what you can do. Anybody have any ideas? Any ideas on what you can do?
I know what you can do, but I don't know what properties of the class.
Okay.
If BC is equal to C, then 3x minus 8 is equal to x plus 12.
Segment BC is congruent to segment CD. How do you know that's true?
The transitive segments.
That's what a midpoint is, right? Doesn't a midpoint evenly divide a segment into two congruent segments? Stay with me, Sumner. Right? So now we got, so that right now you're like, oh snap, I gotta use all my definitions. Every one that we went through already, fair game. Guess what? I'm going to be doing math. So if I'm going to be doing math, I need to deal with numbers. I need to get out of congruence and into equality. Your definition of congruence will help you do that every time. Now I want to go back to what Sumner was saying. If BC is 3x minus 8 and CD is x plus 12, how do I fit them into this story? Anybody have an idea? Maybe that'll help. What do I do? Go ahead.
3x minus 8 equals 22.
I am going to substitute 3x minus 8 in for BC. And I don't know this yet. I can't use that. But I do know that CD is x plus 12. My substitution property of equality, let me put this in for CD and this in for BC. Now might you know what to do? What are you going to do next? Okay. I heard ESCO, which means that this person, like me, likes to group their variables first. So they're going to subtract x from each side, giving me 2x minus 8 is equal to 12. What comes next? Call it out. If you wanted to do addition first by adding 8, you need to make sure it says addition property of equality.
Yeah.
Yep. But Serena's right. She wants to say I wanted to add 8 first. So we'll say 2x is equal to 20. And that's going to be my addition property of equality. Hey, if I say x is equal to 10, what's my justification? My division property. Okay, I've got x. What are we doing? Like, what are we doing? We're doing what? We're, proving the distance from B to C is equal to 22. How do I prove that? How do I prove that? You're super close. So I know that the distance from B to C is 3x minus 8, right? What if I said the distance from B to C is equal to 3 times, and instead of writing x, I wrote 10. What allows me to make that step? Okay, x is the same as 10, so what did I do? Yeah. I used the substitution property of equality, and instead of writing x, I wrote what x is equal to. We're so close, I can feel it. Ready? The distance from B to C is equal to 30 minus 8. The distance from B to C is equal to 22. That, my friends, is you using the order of operations and simplifying. Were you able to say what you needed to? Is that what you were out to prove? We asked you to say, is the distance from B to C equal to 22? And nobody can argue with the thing that you said. Yes, it is. What's on your mind, Sully?
Wouldn't the justification on the bottom be 9?
Oh, very good. Sully, you can put Smarty up. He wants this to say 9. What the heck is that about? Hold on. There we go. How are we doing? All right. So here